So let us move on to a situation where I do not have access to the MDP. I am interested in solving a problem, but I do not have access to the MDP. And this is the most cases, right? Remember, I motivated you about cycling, motivated you with this whole thing about cycling. And what is your PS prime SA in cycling? All of you know what the states are, what the actions are. I mean, we might not be able to enumerate it, but you can kind of have an intuitive feeling about what the states and actions are, but you can't even begin to think of writing down your PS prime given S comma A, right? So maybe you have some rough idea of what the expected reward is, right? So if you fall down, you're bleeding and things like that, so negative reward and those kinds of things, but the transition dynamics are hard to write down, but you still want to solve these problems, right? So I want to look at the whole definition of V pi of S all over again. So what is V pi of S? Right? That's where we started off, right? And then we wrote GT as GT plus gamma, I mean RT plus gamma GT plus 1 and so on and so forth. We started simplifying. But if I had not told you anything else about this whole MDP business, right? And if I told you that this is a random variable, GT is a random variable, right? And V pi is the expectation of the random variable, and I ask you to give me a way of estimating this expectation, how will you do that? Some random variable, I want to find the expectation of the random variable. Sample it a lot of times and take the average, right? That's the most straightforward way of solving this, right? So what we mean by saying sample GT a lot of times? Follow the policy pi. So starts in some state S, follow policy pi until you come to some end, right? And then what do? You add up all the you sum up the reward or sum up the discounted reward, whatever you do, whether you use a gamma or not. I mean, in fact, this here, I mean, I'm not even telling you what the reward is, right? Whether the gamma is there or not is itself a moot thing. So sum up everything, right? That will give me one sample, right? Then what I do, I start at S again. That gives me the second sample. So like this, I draw many samples by executing pi multiple times, and then I take the average. That gives me the value in state S. Is that all I can do with this trajectory? So from S I would have gone to S1, right? So can I use this summation as a sample for V of S1? Why is that fine? Policy is same, and we are also assuming things are Markov. So it does not matter whether I came from S to S1 or from S prime to S1, does not matter. All it matters is I started in S1 and from there on what I did, right? So since I am assuming things are all Markov, so I can do this. So essentially what I should do is I should generate a trajectory first, look at all the states that occur in the trajectory, and then after that take the sum of the rewards that I get and use that as a sample. So what I do is I fix a policy pi, and I am not going to write down the pseudo code for this, please look it up in the book. I am going to fix a policy pi, generate multiple trajectories, okay, and use that to evaluate the policy pi. So I get V pi, right? So we call these kinds of techniques as Monte Carlo methods, right? Because we are in some sense using some form of a simulation to get these samples, right? So I have this model and I run trajectories on that, I get these samples and use that to update the value function. So these are called Monte Carlo methods, right? And so this is a Monte Carlo method for policy evaluation, right? So I did policy evaluation, right? So what are the things that you have to note here? First thing is, I don't really need the model. I don't really need the model. I don't really need the reward. All I need is a way is sampling from that system. Right? I need to be able to run trajectories according to pi. Okay? Correct? I really need to be able to run trajectories according to pi. So all I need is a cycle. Right? I can just get on the cycle and start pedaling around and fall down, get hurt and things like that. All I need is a cycle. So I don't really need you to explain to me what this P S prime SA is, right? So, or if you want to think of it in the herd management case, all you really need is a infinite supply of cows. Okay, you start breeding them, you see what happens to them, and then you know that you can solve it, right? So when sounds kind of gruesome, but you could do that, right? So that's essentially what we are talking about here. Okay, but you could also get by without the real system, right? I don't give you an infinite supply of cows or something, but I give you a simulation model. So what I mean by a simulation model? Let's give you an example. So how many of you have written programs to play games? Anybody? Like play card games? Okay. So how many of you know about the game Blackjack? It's an example given in the book. How many of you have heard of the game Blackjack? Really? Heard only. I'm not going to ask you to play here. Don't worry. Okay, so it's like, how many of you saw the movie, 21? Yeah, everyone says, then you have heard of Blackjack. Now they are more confident of putting their hands up when they said, how many of you seen the movie 21? Don't worry, I'm not going to play the movie here either. So, it's a card game where you deal a hand of cards to people, right? And then people start turning over their cards, and then they have to make sure they get as close as to 21 as possible, right? So, the state space would be what? What cards you see, right? What cards has your opponent has, right? So you know the first two cards, then you know your cards, and then you can keep going if you want or stop, right? Do you see your opponent's cards? Don't you have to stop before you see your opponent's cards? Huh? You have to stop before you see the opponent's card, right? So you don't see your opponent's card, right? So you see whatever cards you have and then keep going. And what are your actions? Yeah. Huh? What's it? Flush. No. Is it? No. I'm not talking about poker. I'm talking about 21. Yeah, blackjack. Yeah. So essentially, it's hit me or stay. Right? Again, that's not. Stay. Stay means you don't do this. So hit me means give me one more card. Right? So that's all. The two actions: either continue or stop. Right? So that's basically it. So it's a very simple problem. Right? But now, if you want to think of it as okay, what is the probability that the next card I flip will be an ace? What is the probability the next card I flip will be a king? Right? And then it becomes a little tricky. Right? It's right. So you have to do this on a specific game, right? And then what is the probability that the opponent will win, given that these are the cards I have turned over? Ouch! Now you have to come into your combinatorial summation. Right? What are the many different combinations that the opponent can flip over, and that will actually be controlled by what cards you have already flipped over, right? So this becomes a little tricky. On the other hand, suppose I ask you to write a computer program that will play 21 with me or blackjack with me. It's a fairly straightforward thing, right? You just need to keep track of which cards you have dealt and then randomly sample from the other cards and then give it. So I can write a program that will play blackjack with me much easily, right? Much more easily than actually writing a program that will compute that P S prime S comma A for blackjack. Right? So such models are called simulation models or sample models. Okay, this is allow you to generate samples, but they are not a full specification of the transition probabilities. Right? So I can run these Monte Carlo methods with a sample model. I don't have to use the sample model to compute my transition probabilities. I can just leave the sample model. I can run Monte Carlo methods with the sample model. So that's one of the nice things about Monte Carlo methods. Right? One thing which I want you to note here is the samples I draw, right, the trajectories I run here, not only pick the states at which I will be doing the evaluation, they also give me the value with which I will be doing the evaluation, right. This expectation, right, so whatever the expectation computation, that is also determined by the sample I draw, right. So here when we did trajectories, we were only using them for picking the states, but the updation was using this kind of a recursive evaluation, right, using the model. But here the trajectories I draw not only give me the state, but they also give me the rewards with which I am updating the value of the state. Is it clear? Good. So this is called Monte Carlo policy evaluation. Is there any other question that you want to ask me here?
Sir, the pi is stochastic?
The pi could be stochastic.
Could be or should?
Why it should be? I am evaluating a pi, right? I am only interested in evaluating the pi. Why it should be? If pi is deterministic, you need to do one small additional thing. What is that?
We need the probability of getting an answer.
We do an expectation over all the possible from this.
Very, very simple. I am talking about very practical things here. Huh? I have a fixed pi, okay. Look, when I am talking about policy evaluation, I have a fixed pi. There is no greedy, no nothing business, okay, no exploration business. If I explore, the policy will change, right. I'm giving you a fixed pi. If I'm going to explore, then that if the pi is probabilistic, then already I'm doing some kind of exploration. Stochastic, I'm doing some kind of exploration. If the pi is deterministic, even if you explore on the pi, then it's no longer pi, right. I'll come to that case later, but this is a good point now. So what should I do? I'm interested in finding V pi of S, right. If I'm only interested in a small subset, then it is sufficient for me to start my trajectories only from that small subset. But if I'm interested in finding the value for all the states in the MDP, then I will have to make sure that I at least start from each and every state, because it's a deterministic policy, right. I have no guarantee that the states would be visited, because it will be only a specific trajectory that I will be following repeatedly, right. There is no guarantee that the states that I don't start from will ever be visited for me to get samples from there. So I have to start from many different states so that I can get samples from those states, okay. So in fact, even if it's a stochastic policy, you will have to do this exploring starts, because there is no guarantee that you will hit every state even with the stochastic policy, right, unless the policy happens to be something that allows you to explore the entire state space, like a random policy, like a completely random policy. Every state I pick an action with probability half or whatever, 1 by n. So I have n actions in each state. I pick each action with probability 1 by n. That essentially means I will end up covering the entire state space. Provided
I have it in front of me.
huh?
I have it in front of me.
No, provided the entire state space is reachable, you know, I mean, so I can have a grid world like this. That's a wall, right. So everything here is, I can go, everything here I can go. So if I start from here and go, even if I'm acting randomly, there is no way I'll go to this part of the world, right. If I start from here, even if I am acting completely randomly, there is no way I'll go to this part of the world, right. So they are not reachable from one another.
How do you find those ranges?
What's that? How do you find?
Those ranges?
Do you need to? Is a question. So if you need to, there are ways of doing it. For smaller problems, for larger and larger problems, they become not very tractable, right. So you can use techniques from dynamical systems, you can use techniques from physics, you can use techniques from graph theory, depending on what is the setup that you are interested in solving, right. Right, so where were we? So sample models, then exploring starts. So that's one other question that I am expecting people to ask me. Nobody is asking me that. I start from S, I run a trajectory. So I use the trajectory value for updating the value of S. Okay. So what if S appears again in the trajectory? This is 2 trajectories starting from S or 1 trajectory starting from S? Why is it 1? When we started from S, I said if the next state after S is S1, then we can consider that as a trajectory starting from S1, right?
You get 2 updates in that.
Huh?
Possible at all because
You'll
you
stop
keep
it at-
getting S again and again.
Not necessarily, right? We're talking about probability of transition is there. Even if I'm using a deterministic policy, there's a probability of transition, right? So I might come to S and then I might skip and go out of S the next time. That's possible. Okay. I mean, here's a simple example. So I have S. Only one action from S. Okay, I do that. So 20% of the times I'm going to come to S and then I'm going to stop. Right, so S, yes, stop. Yes, 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 stop. So that's how it's going to look like. It's possible. Which is correct? 1 trajectory or 2 trajectories? 1 trajectory. How many of you say 1 trajectory? No. My question was how many of you say 1 trajectory? Either put your hand up or don't put your hand up. Okay. So many said 1 trajectory. Yeah, only 1 person is putting his hand up. Okay. How many of you say 2 trajectories? What about the rest? 8 trajectories, is it? 0. You have to have an opinion. I'm going to start from 0 again. So I'll keep going until everybody put their hand up. 0. Oh, okay. 2. Okay. Turns out both are right. 1 and 2. Right. So when you do 1, it's actually called first visit Monte Carlo. When you say 2, what is it called? Huh? Close. Can you be better than that? Right. So if you use only the first occurrence of the state, it's called first visit Monte Carlo. If you use every occurrence of the state, it's called every visit Monte Carlo. So when I say you use the first occurrence, what does it mean? So I take the return occurring after that, right? The entire thing, I use that as one sample for updating V pi of S. When you say every visit, that means I take the return after every occurrence. So right, so the first return will be this much, right, and the second return will be this much. Okay. So what is the real problem here is that when I do every visit Monte Carlo, I have just taken one sample trajectory, right, but I am using the sample trajectory twice. At least part of the sample trajectory I am using it twice. Okay, why is that a problem?
The V-pi gets updated for the same square.
Yeah, so why is that a problem? So when I approximate an expectation with samples, I am assuming that the samples were drawn according to the distribution on which I am taking the expectation, right. So the distribution yielded me this one sample once, right, that one trajectory it yielded it once, but I am using it twice. So essentially I am changing the distribution. Right. So that is the main problem. So I am not using the same distribution that I am taking the expectation with respect to. But it turns out that all this adds is a little bit more bias estimation, right? When people remember bias variance trade-off, but it's not very important to know if you don't remember bias variance trade-off or never heard of bias variance. So it introduces a little additional bias into your estimator, but it turns out that in the limit, right, if you do a lot of samples, in this particular case it turns out both converge to the same value function. So it's fine.
So can you explain how it changes the underlying probability?
See, I roll the dice and take a sample, right? I mean, so essentially I'm for every step I take, I roll a dice, first pick an action according to my pi, then I pick a next state according to PSS prime A, and then I pick a reward according to the expected reward, so on and so forth, right? So I do a lot of simulations. So a specific trajectory has now appeared. So S1, S2, S3, S4, and then for each one of these I get R1, R2, R3, R4, and I would have picked actions A1, A2, A3, A4, right? But then how many times this kind of a thing occur should be determined by rolling the dice again and again, or rolling my coins again or whatever, right? Tossing the coins again and again. But I didn't do that, right? I just generated this one sample once, and I kept saying, okay, so this part is one sample, now this part is another sample, this part is another sample. So for one roll of the die, I am just taking multiple subsections of it and then repeatedly using it, right? So if I had started from S here and rerun the experiment, right, I might not this might not be the one that I produced, right? I will actually produce something else again, right? So essentially that's the tricky part. That's why I'm changing. That's why I'm saying you're changing the distribution to some extent. Huh? What's it? It shouldn't hurt. That's why I'm saying it will eventually converge to the same thing. So if at all there was a thought about why you shouldn't do every visit, that was the reason. Oh, it affects in some sense, but how do I put it? Let's say that there is something here that happened, right? That is very, very rare. Very, very rare. It occurred once, right? It will probably occur once in a million times if you have actually run them independently. It occurred once on this trajectory, but you are going to count it twice. Once for this S, once for that S. Right? But if you had drawn independent samples, it would have happened only once every million trajectories. Now it is happening twice every million trajectories, which is a significant change. In some sense, you double the probability of it. Okay, so that's basically. So that's why it could be a problem. Using every visit MC could be a problem. Okay. So good. Any questions on this so far? I think we have covered all the things I wanted to do. So Monte Carlo, you could do sample models, exploring starts, first visit, every visit.